Excellent. I see we've got incoming news from our friend in South Africa. Totally failing to understand what trilateration is. And now another has joined the fray. Flatsoid FE. So my little South African friend, take it away. In recent weeks, flat earthers have been in all of a kerfuffle about sextants. They seem to think that a sextant proves the earth is flat and that it can't possibly be a globe. If you're going to try and debunk sextants that absolutely require the earth to be a globe in order to work... Why is he laughing? Why are you laughing? If you're going to try and debunk sextants that absolutely require the earth to be a globe in order to work, that when you're doing celestial navigation with a sextant, you're not using triangulation. And why is she laughing? Why is she laughing? That when you're doing celestial navigation with a sextant, you're not using triangulation. That when you're doing celestial navigation with a sextant, you're not using triangulation.
Sextant. A sextant is a navigational instrument that uses a telescope and an angular scale to calculate the latitude and longitude. Making a measurement with a sextant is called sighting the object or taking a sight. The optical instruments called sextants have been used as navigation aids for centuries, especially by seafarers. The sextant replaced the astrolabe, which was used in ancient astronomers for navigation. And its simplest form, a sextant consists of an eyepiece and an angular scale called the arc, fitted with an arm to mark the degrees. By manipulating this part, a user can measure the angular distance between the celestial bodies. Remember that keyword, angular distance. Usually Earth and either the Sun or the Moon. The observer can thereby calculate his or her position of latitude by using a trigonometric operation known as triangulation. Whoa! The word sextant derives from a Latin term for 1/6 of a circle or 60th degree. This term applied to generally be a variety of instruments today, regardless of the spans of their arcs.
Doing celestial navigation with a sextant, you're not using triangulation. Well, I made several statements about sextants and celestial navigation, triangulation, trilateration, every one of which I stand by 100%. So I don't know why you've got all this inane laughter. That when you're doing celestial navigation with a sextant, you're not using triangulation. Come on, it's about time you got on with it, Flatsoid. What is the nub of your gist?
What did he say?
What has trilateration got to do with using a sextant? Well, Flatsoid, if you're going to carry out celestial navigation, it has everything to do with the sextant. Aha, the difference between triangulation and trilateration.
I don't know about that, but I do know that I love fluffy little kittens.
Well, Flatsoid, I'm holding out less hope of you understanding that than I have of receiving a phone call from Kylie Minogue demanding that I become her plaything.
What is triangulation?
A good question, and one that has been much on my mind in recent weeks.
Mr. Sensible, you do understand. You have a point. You have the luminary, which is the sun here.
Ah, Flat Earther's measuring device of choice. A crayon.
And you have the zenith, which is the GP. This creates a triangle.
Well, two things, Flatsoid, spring to mind. Firstly, the zenith is not the GP.
The zenith points out the GP, as you have a zenith on top and a nadir, which is in the bottom. You know, when you move your GP, then you have a new zenith and a new nadir. So yes, your zenith is definitely pointing your GP.
The GP is the point on Earth directly below your zenith. Secondly, we don't create triangles.
Yeah, you're right. I must be imagining this triangle, or how about this triangle? Or maybe this triangle, I'm imagining it.
But let's run with it. We'll assume you're flat Earth. You show us triangulation.
With a sextant, you are using triangulations. You have an A, B, and C. The 90 degree from the zenith and your angle towards the luminary. Triangulation.
Flatsoid, because you have a triangle on the screen doesn't mean it's triangulation. With triangulation, you need angles to several known positions. All you have on the screen is a triangle. With this, you're not even solving a triangle. Let's see what information you've got. You've got your viewing angle, the angle of the star above your horizontal at A. Let's say it's 45 degrees. You have B, the position of the star. Directly below it, you have its GP at C, which is 90 degrees to the horizontal. So what have we got? We've got 45 degrees to the star, 90 degrees at point C. We don't know how far it is from A to C because that's the distance we're trying to work out. We don't know how far it is from A to B to the star. We don't know how far it is from B to C, the height of the star. So basically we have no sides of the triangle. So go ahead, solve that triangle and give us length A to C. You can't. You do not have the information. That is a total fail. And even if you did, that's not triangulation. That's just solving one triangle.
Right, where do I start with how wrong you actually are? First of all, triangulation requires you to be able to figure out something based on the angle. What do you think A is? It's the angle to the luminary. That is triangulation based. Now, Mr. Sensible, you've taken that, let's say, 45-degree angle to B. You have the time that you took it to there. So you look in the almanac and now you see, it is 5 p.m. I see this star and this with this amount of degrees. So obviously the circle of equal altitude based on the time the star is seen from this angle, let's say, is 900 to 1,000 miles away from me. You have just debunked your own self telling me you cannot triangulate with one triangle. Mr. Sensible, what do you have to say for yourself? Now, if you want to be more accurate, you can do more than one observation and therefore do more and more until you get your exact pinpoint location, aka triangulation, done with one triangle.
So what is triangulation then, Flatsoid? Well, that's when you don't know your distance to various known positions, but you know the angles to them. So what is triangulation then, Flatsoid? Well, that's when you don't know your distance to various known positions, but you know the angles to them. So in this case, we're somewhere in the wilderness. We sight a mountain, landmark 1. We read its bearing. We then take our map, find landmark 1 and draw that bearing line on it. We are somewhere along that line. Then we do that a couple more times. We mark up all the bearings on the map. Where they cross is your position. In this case, there's a little triangle because of error, so we're somewhere in that little triangle. That is triangulation.
Yes, Mr. Sensible, that is triangulation. Congratulations for using angles to triangulate. That is the whole point, measuring angles to triangulate your position, thereby creating triangles with a flat baseline. And by the way, that line is 180 degrees. Do you know that that means flat baseline, not curved baseline, Mr. Sensible? You might want to look into that. What is trilateration?
Trilateration, another good question that has also been much on my mind in recent weeks.
Well, first of all, Mr. Sensible, you would actually need a receiver.
Flatsoid, you've been listening to too much 10th Man, haven't you? Yes, you can use signals and receivers to trilaterate, such as with GPS. But you can trilaterate using distances however they were obtained. You do not have to use any sort of electronic broadcast.
That's correct, Mr. Sensible. You do not need it to be electronic, but based on today's age, it is only done electronic, because you're not going to get someone going in the Navy going, we have to look for a landmark so we can trilaterate our position known on these known landmarks, do they? And you would need some kind of tower sending out a signal. This tower sends out a signal that moves with a certain radii.
Flatsoid, it doesn't move with a certain radii. The signal expands outwards in a circle. The radius is increasing all the time.
So you take what I said, say exactly the same thing, just change the wording and then want to say that's not what I'm saying. Doesn't sound very sensible to me. This circle of equal altitude will ping as soon as it hits your receiver.
Now, I don't wish to appear churlish, but one does feel a churl coming on. Flatsoid, I think you perhaps have little idea of the things of which you speak. A circle of equal altitude is the circle around the GP of a star where that star appears at the same altitude. Equal altitude.
May I present to you your globe? Do you see the problem with equal altitude? No, not yet. Let's zoom in and see. How about now, Mr. Sensible? Is the center of your Earth to the surface the same?
And it turns out sea level at the equator is farther away from the center of the Earth than sea level near the poles. And it got a little wider at the equator than it does at the poles. So it's not actually a sphere, it's oblate. And officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped.
Yeah.
So
You cannot get an area of equal altitude on your geoid, as the center of Earth is a different distance away from the surface.
It has nothing to do with radio signals.
A sextant does not have a receiver,
Yay, he got something right!
therefore it's not trilateration.
Oh, bugger.
Now you have 3 towers emitting signals.
Then shalt thou count to 3.
They move towards the receiver. As soon as they hit the receiver, you will receive a ping. Let's take a gander. There they're moving out. Ping! Ping ping! And that is how you work out with trilateration, the distance from the emitting towers.
Well, I have to give you that, Flatsoid. That is trilateration. It is one form of trilateration. Those signals could be coming from towers. They could be coming from GPS satellites. With both of those, the timings of the signals give you the distance. You draw circles around their known positions and trilaterate. But you can use any method to get those distances. I could use a sextant, take readings from 3 stars to get their distances in nautical miles.
I wonder how you got those distances. Maybe your angle towards the GP.
Mark their GPs up on a map, draw 3 circles around them, and trilaterate. With celestial navigation using a sextant, we're not triangulating.
Crash, great.
Hell, we're not even calculating and solving a triangle. That when you're doing celestial navigation with a sextant, you're not using triangulation.